using this choose power.
There's an outlet here you can use.
It's UIT with all these trick outlets. Okay, this one. Okay. And we also were able to characterize the square value, the noise. This was 2k zeta epsilon ij, where those are the computed coordinates, and epsilon t minus t. Those uncorrelated in time and uncorrelated between orthogonal and Cartesian directions. Okay, this is a second order equation. Okay, it's first order in B, but ultimately we're interested in the position, and this is second order in the position. All right? But we want to make a first order equation here. What we're going to do is draw the inertial term here. Okay? So we're going to set it equal to 0.
Or what's the last equation doing?
What's this equation doing?
Are those components of R, or
So yeah, it doesn't need a dot in here.
and there's no vector?
And there's no vector.
Okay, right.
Okay, so what is the physical interpretation of dropping that inertial term?
Over down.
Okay, can someone be smart and tell me what that means? Yeah, well, what does overdamped limit mean?
It means that if we happen to have any inertia, it's immediately dropped out, goes away. So
Yes.
I guess you could say it's like trying to swim through a super thick liquid. If you
Right.
get pushed really hard, it goes away. Like it doesn't matter.
Right. So remember what this differential equation says. It says rate of change of your velocity proportional to negative the velocity here. Okay. So what this means is that you'll accelerate for a while until this drag term equals your acceleration term, and you're at terminal velocity. Then you have no net acceleration. Okay. And what the overdamped limit says is that that happens very fast. You basically reach terminal velocity instantaneously as soon as you get a kick in that direction. Okay. So this means we can simplify our equation to theta b was our t. Which is very nice and simple. And if we wanted to solve this, what could we do? We could say keep the integral with respect to time of both sides. But now we run into our usual problem with stochastic differential equations. Right? There's no general solution for this because your random term is random. Cool? What do we do whenever we face that? What's the way of getting out of this? Yeah, we take the average, okay? Let's take the average of both sides here. And so this then just becomes the average V. This is the average R. And what does that equal? If you average over all your random numbers, you get.
Yeah.
Right.
Does that really tell us anything? Oh wait, it would be self-offset.
Cool?
That's in the long. No, it's not right. Yeah.
No. So in fact, this tells us that the average velocity is 0.
Yeah.
Cool. All right, that's not super interesting. What if we try take the square? Okay, and I'm going to take the square. We're going to do it over two dummy variables, t prime and t double prime. And we've done this before. So we'll see like it's even easier when we're at this scale. When we're dealing with the first order.
Second down integration be equal to 5 or something.
Where?
We're integrating from 0 to t both times, but
Yes.
0 to t prime.
No. Because really these are, we're just taking a square, right? So we could set this. Right. Yeah. Cool. What is this equal to? Left hand side.
Just be like average velocity.
Have it where
Average velocity.
we're integrating that, right?
The autocorrelation though?
This, you do this integral, okay? What you're going to get if you do one of these integrals, you're just integrating the velocity with respect to time, right? You're changing position, right? And we have that integral squared. This side is just equal to delta r squared. Okay. And on the left-hand side, what I want to do is say, okay, this thing, let's do it in 3 dimensions. It breaks up into 3 individual integrals, double integrals, each one of which we expect to be equivalent, X, Y, and Z. So let's just say it's equal to 3, 0 to t, at prime, 0 to t, at double prime, and let's put in what we know about the character of the noise. Okay, we know that this is equal to 2 kt zeta, and then delta function t minus t prime.
I think I missed something. So we're doing a double integral over 2 velocities because we're going to 2t.
No. So what we're doing is, so to get here, do you understand how we got here?
No.
Okay, so we have this equation, right? Cool, you understand how we got here.
Well, that's where we were starting from, right?
Well, we're really starting from with the first order Langevin equation.
Yeah.
Which is,
But then we reduced it down to there.
yeah, we did the integral of both sides. Then we said, oh, we can't solve for that, we have to take the average. And
Yeah.
we took the average, which is equal to 0.
Yeah.
Instead, what we're doing is we're squaring both sides. Okay.
Okay. So why do we square it again?
Because that is how we can get, because the average of this is 0, that's trivial. Okay, like remember the average of our noise is 0, it's trivial. But
Okay.
the average of the square has information. Okay, so what it basically says is if you do a distribution of your mean of your random numbers, they have a mean of 0. Okay, but they have some finite width. Okay, and that width, that variance of the distribution, is given by this. Cool. And so we're doing the exact same thing here. We did the same stuff with the Langevin dynamics. Cool. So that's how we get here. Yeah. We're just expressing it in a funky way here so that we can get back to this form here and we can solve this step. Cool. This side, if we look at it, all we have is 2 integrals over these velocities here, right? And it really is just a square. the integral of the velocity with respect to time is the position, the change in position delta r. And so we have that squared, so that's what the left-hand side equals. Cool? Yeah? Okay. Let's at least pretend that's cool for now. See what happens. Okay, so what we can simplify this a bit. We get zeta squared delta r squared equals 6 kt zeta. And now let's look. We have a double integral here. But in the argument of our integral, we have delta t minus t prime. So if we integrate that over t prime, what do we get?
Only under the circumstances that t delta prime is equal to t prime to be 1. Everywhere else it should be 0, right?
Yes. So the only term that survives is when t prime equals t double prime. Cool. So all that does for us is it kills one of these. Okay. What do I have left? Nothing. Yeah. Cool. Okay. This means we can solve that delta r squared is equal to 6 kt zeta t. Sorry. I'm going to bring the zeta over to this side. Does anything in here look familiar? Yes, no, maybe? Yeah, well, how about the kt over zeta? D, that's a diffusion solution, right? So we have derived is equal to 6 dt. How many dimensions are we in? 3. So 2 little d, big D. Okay, which should seem very familiar to you. This is an Einstein relation for diffusion. We got this out of Langevin dynamics, but remember, this is only true in Langevin dynamics when? Yeah, the long time. Okay. Why? At the short time limit, we had ballistic motion. Why? Because of the inertial term. If we drop the inertial term, do we ever have ballistic motion? No. Okay? It's diffusive the whole way. But we've dropped the inertial portion. Okay? That is the difference between first order Langevin equation and second order one. Cool? Any questions on that?
So we kind of come to the exact same thing we've done before in the long time limit.
Yes, but now we didn't have to take the long time limit.
Right.
Okay, this is always true for first order.
But isn't, like, if I look at the first, or if I look at any kind of overdamped limit, if I kind of view a time frame super, super tiny when something gets a kick, couldn't I still argue that it's still ballistic for a super short time period? So doesn't it just become the second order whenever you're looking at these things?
Yes, so that is a very good. Okay. The thing is that usually, the vast majority of cases, Langevin dynamics and Brownian dynamics, which we'll see as the simulation of this, give the same result. Okay. However, they strictly are not equivalent. And we'll talk about this in a minute. It doesn't matter. Like, you can say, okay, well, we got this by dropping the inertial term. The inertial term was ma. So I can just say that as my mass goes to 0, I go from Langevin dynamics to Brownian dynamics, right? And what that does is it shifts the transition from ballistic to diffusion in very, very short time. But it is never exactly 0 unless you exactly set this. And in the physical world, there's always going to be this little bit of time that there's a finite acceleration. And in some cases, you get very different results between Langevin dynamics and Brownian dynamics in the simulations. Okay? There are some cases where that little bit of acceleration, no matter how small, really matters. Dan, can you think of it? The case that we have is a particle at a viscosity interface. Okay? If you do the simulations between Langevin dynamics and Brownian dynamics, where you start a particle and one half of the system is like water, it has a high diffusion coefficient, the other half is like honey, has low diffusion coefficient, you get totally different answers from Langevin dynamics and Brownian dynamics. And it's because of that acceleration as it crosses the interface, it matters whether it's there or not, no matter how small. Okay, that is also a good project for this course. Diffusion in homogeneous medium. Okay, that only some. Matt, well, he's not in the course, but he couldn't even do it. Okay, because that's what his research is.
So if you were
Dan also couldn't do it if he was.
If you're looking at diffusion of photons and some kind of optical medium and trying to do it this way, or like bouncing out of nuclei, bouncing off, then you could physically take that. Emission. They never accelerate, right? That would be a physical system where.
Sure. Yeah. For sure. Yeah. But in most cases, but it usually. Yeah. Although, yeah. Okay. Okay, so everybody's cool with this. So this is an answer we've seen a bunch of times. It was actually very easy to derive here compared to when we had to do this in Langevin dynamics. Okay? All right. The other nice thing about the first order equation is that there is a completely equivalent way of expressing this, not as a stochastic differential equation, but as a partial differential. Okay? And so remember where we're starting. We're starting from okay, so this is our very simple stochastic differential. Okay? Let's talk about an equivalent PDE. Okay, now there's a way to formally go from this to the PDE. We're not going to cover that. Okay, that's more serious math than I want to get into here because I want to get back to the simulations of this. That is also a good topic for a research project. Okay, at least part of the research project. So formally investigate how you go from an SDE to a PDE. Okay, because one way we're handling with our SDEs is to just average over them to get rid of the noise. Okay, you can also do this. You can transform it into a partial differential equation and then look for a solution. Okay, and what you do is you end up going from looking at the behavior of individual particles to instead looking at the behavior of the distribution. Cool. Well, the SDE gives us how we can describe how any one of those particles might move around. The PDE tells us how the distribution of those particles will evolve. Okay, so we're going to go through that now and see that these are totally equivalent to each other, but we're going to do it numerically. Okay, but first let's just introduce what PDE this is. Anyone want to guess what PDE this stochastic differential equation? A very general class of PDEs. That will be the solution to the PDE. But the PDE itself, right, the different classes of PDEs, what this is going to be. Those of you that had me in third year did an entire course.
Maybe parabolic.
Not the wave equation.
Yeah.
The heat equation, but really the heat equation is a special case of no.
Parabolic.
Fusion equation.
Oh, right.
Okay.
No, the thing other.
Wave equation with infinite.
Yeah. Cool.
Yeah, the characteristic velocity.
Okay, well, let's talk about that later, okay? It's not the wave equation. It's a diffusion equation, okay? The heat equation is a really special case of the diffusion equation because heat travel by diffusion things, okay? Cool? All right. So, how can we get the diffusion equation? Well, just to remind you of a simple derivation of it, we can start with a continuity law. And this says that the distribution, some group of particles, how it evolves in time, is going to be related to the divergence of those group of particles. Okay? Which makes sense. So how those things, the character they have of how they might, like, remember divergence, how you're spreading out. Okay? So that is going to be equivalent to looking at how the distribution of particles changes. Cool? This is just a continuity law. These must be. Okay. But remember, Fick's law, it tells us, and in the most general terms, it tells us that if we have a distribution that is not continuous, there will be a flux of particles, basically in negative the gradient of the distribution. Cool? What is this telling us? It's telling us we have a distribution of particles like this. We have way more particles here than we do on either side. Okay? So there's a gradient here. This would be a negative gradient. There will be a flux in this direction. Okay, here, there's a positive gradient. We'll have a flux in this direction. That's all Fick's law tells us. Okay? These will be proportional to each other. And how will they be proportional to each other? There's some constant there, and that constant is the diffusion. Cool? And in general, the diffusion coefficient can change with the position and also with the current density of particles at that position. Okay? Well, this can be very, very complicated. We're going to make a simplification, which is that d is constant. Okay, we're going to make that a simplification. All right, and we'll see why that's important right now, because what I can do is I can write down time derivative of rho is going to be the divergence of this current, which is the what I've written here. Okay, and this is the diffusion equation. Because we have time derivative over here, and then we have a gradient, which is spatial, and a divergence, which is spatial over on this side. So we have a partial differential equation. Cool. And it relates the spatial behavior of the distribution of particles to the time evolution of that distribution. And the only constant we have in here is the diffusion coefficient. This is our diffusion coefficient. Cool.
What happens if it's not a constant?
That's when things get interesting. Okay? And I should be more careful. So what happens when it's not a constant? So first of all, let's look at what happens when it is a constant. Okay? If d is a constant, this reduces to d, the Laplacian of rho. So let's put that together. Okay? And so now we have a nice, tidy differential or partial differential equation. Okay? When d is not constant, you can't make this simplification. This is as far as you can go. Okay? That's why when you have things like diffusion in an unhomogeneous media, you have to be very careful how you solve. Okay. That's where this gets tricky. Cool. Yeah. Okay. So ignoring the inhomogeneous media, which is a really cool problem, and I can send you some things. Okay. One of which is massive and is stuck on archive. What is the solution to this differential equation? Sarah? You knew a couple minutes ago.
Oh.
It's a Gaussian, okay? So if we take x naught for all the particles, okay, will actually be equal to 1, such that our distribution at t equals 0 is just equal to delta x. Okay? So starting all the particles at x equals 0. Then the solution with this initial condition in this partial differential equation is rho of x t equals 1 over 4 pi d t e to the negative x squared over 4g. And I will leave it as an exercise for you to take this and plug it into the left-hand side and right-hand side and make sure you get the same result with the d. Cool. Okay. Let's take this to be the solution. If I want to calculate the mean value of x, and I have the distribution in x, how do I get that? Not Martin. So I have the distribution of x, okay, at every time, okay, because that's what it's equal to. And I want to calculate the mean value of x. How do I do that? So basic statistics. Yeah, okay, so you integrate over all space. We're doing this in one dimension, so this is negative infinity to infinity. Of x times rho of x t. Does this make sense to people? Do you see why this relation is true? Okay? Think of it this way. You have a histogram, okay? People of various heights. Okay, these are people that are 3 feet tall, 4 feet tall, 5 feet tall, 6 feet tall, 7 feet tall. Okay? And you want to calculate the average height of people. How do you do it?
Take all the 3, 4, 5, 6, and 7, add them up.
You just add up 3, 4, 5, 6, 7.
Like how many 3s? How
Right,
many
so you
4s,
go-
how many 5s?
I have this many people who are 3 feet tall. I'm going to add to that this many people who are 4 feet tall. So I have 3 times this number, plus 4 times this number, plus 5 times this number. Cool? Add them all up, and I divide by the total number, and I get the average height. Cool? Now shrink this to 0. What are you doing? You're just integrating over this distribution by multiplying it by the variable you're interested in. That's all we're doing. Cool? This is just a continual limit of this. Fair enough? Okay. So if you actually plug this in, and again, I will leave this to be an exercise. What do you think you get? Not one. Should give you. We're looking for a number here, right? Now, well, it could have time dependence in it. Okay. We're basically looking for some function of time dependence. Okay. So remember, we started all the particles at 0. Okay. Oh, this is what we do. Not 1. So we start all the particles at x equals 0. So at t equals 0, I have a spike here of n particles. Cool. The way this distribution evolves in time, okay, is a Gaussian in x. So if I look sometime later, what's my distribution going to be? Yeah, it's just going to be spreading out, right? Cool. So as time grows, what's happening? Well, actually, we see it explicitly. This is the variance, right? 2 times the variance. The variance is just growing as 2dt. Cool. So at t equals 0, what's my average exponential? 0. At t equals not 0, what's my average exponential? 0. Okay. Plug this into Wolfram alpha, you'll get 0. Cool. Yeah. Okay. In fact, this method works for calculating the average of our observable x to any power. Okay, if we want the average x squared, we just again integrate over the distribution, but now we multiply by x squared. We can do the same thing for the cube, the fourth, for the fifth, doesn't matter. Cool. This is one of the beautiful things about knowing your distribution.
Isn't the square position average not 0?
No, not true.
Oh, yeah, right, yeah. Okay, I was going to say, like, wait a minute, I've been lied to.
Yes, you have. Okay, cool. Again, put this into Wolfram alpha, or solve it in Martin. We get 2dt. Right? So we're doing this in 1 dimension, so we have our x squared is equal to 2dt. That's not the same thing we had before. What we had before was that our delta x squared is equal to 2dt. But since our average x is equal to 0, this is equal to our delta x. That's what we have. Cool. Well, how else can we see this? In fact, we already knew this, because if we have a normal distribution, a Gaussian distribution, the general form is 1 over 2 pi sigma squared e to the negative x squared over 2 sigma squared. What's sigma here? Standard deviation. Yeah. Okay, sigma squared is the variance. Cool. And so, what does this tell me? It tells me that sigma squared is equal to 2d. Okay? So this is the dispersion. This is how the distribution is spreading out. Cool. And of course, that agrees with this, because this is also the dispersion, how this is spreading out. Cool. Well, it's more than just a linear function. Okay. This is a mean square displacement is linear. What kind of motion has that? Diffusion. Okay. Remember, if this was ballistic, this would go as t squared.
Like cool. A lot of p's.
Everybody all right with this? Okay. Everything is nice and consistent. So we have a stochastic differential equation where we can actually simulate the trajectories of individual particles. From that, we can calculate a distribution. But we also know what that distribution must look like as a function of time, because we can recast the SDE as TE, and we can solve it for the simple case. Cool. So let's see if this is actually true. Well, before I do that, I want to talk about the feature. It's not the plan. Talk about one other relationship. Okay, the Einstein-Smolakowski equation. Okay, let's take a single particle, and this is experiencing some force due to an external potential. Okay? Well, the force, we'll just do it in 1D, okay? Right in X. The force is, of course, negative the gradient of the potential. In 1D, this means the dBx potential of Ux. Negative. All right? So F equals ma. So what is going to happen? We're going to reach some velocity. And that velocity is going to be proportional to the force. Okay? And the proportionality constant is mu, which is the mobility. Cool? So if we take a whole bunch of particles in a system, and they're subject to some potential U, what is the equilibrium state of these particles defined? StatMech. So do they all just go to the minimum of U?
What are you, sorry, what are you? Yeah, just one state.
Okay, so we have, sorry, I'll be more clear, okay? We have a bunch of particles in a box, okay? They have some temperature T, which corresponds to some average kinetic energy, right? We have some potential applied to them. Let's say it's a force down, such as gravity, okay? So we put them in the box, then we turn on gravity, wait a long time, we come back and we look at our box. What does it look like? Are the particles evenly distributed throughout the box? No. Are they all at the bottom because gravity is forcing them down to the bottom? No, because they have this thermal energy, right? So there's a probability they'll end up going away. Cool. So there's a net distribution. What does this distribution give about? Anybody?
Ultimate distribution.
Thanks. I guess I didn't say not, Mark.
I said sideways.
Isn't what you triggered inside?
Okay, you're going
Okay, so why is a mathematician in a room full of physicists giving me the answer here? Okay? Well, not because there's another math guy in there. We're very diverse. Okay, so yes, it's given by the Boltzmann distribution. What does that say? It says the density at any position x is going to be proportional to E of the potential at x normalized by the. Cool? You guys have seen this before, right? Yeah? Yes.
With the potential. Austin, you saw it over the summer.
Yeah, you've been
We've never seen this.
We've seen both things,
I
but
can-
I don't know. This is very schoolish. Remember. This is-
Elizabeth, you're saying no? You don't think
I don't
so?
remember that.
You can't say yes.
If you saw it once, 2 or 3 years ago, then you would remember.
Okay, so maybe that's something I'll try and find some resources on so you can refresh. Like where this is. Okay, this is just, yeah, this is something you gotta have in your back pocket. Okay, all right. So if we have this system, okay, are things static here? So that if I look at my distribution, I get this, okay? Does that mean each particle finds its position and more of them are at the bottom, but there's some near the top and they'll just stay? No, okay, they're always moving around, okay? So it's equilibrium. But what we have is dynamical equilibrium. The particles are bouncing all around. In fact, there are fluctuations in the distribution, but on average, this is what it looks like, okay? And in fact, we have two currents in our system, okay? The one current we have is the drift current of gravity pulling the particles down, okay? I'm using the example of gravity, but this can actually be much more complicated than just being linear in whatever dimension, okay? So that current, let's call it the drift current. What is that going to be equal to? Well, if we pick some point x, the drift current is going to be the velocity of the particles at x multiplied by the number of them at that position. Cool. All right. Well, this guy we can express as u the mobility. So u the mobility multiplied by f of x, rho of x. This we can say is negative rho of x, mu du dx. Okay, so that is our current of particles due to drift, in other words, due to the external potential. Okay, we must have another current, right? Because if this was the only particle current in our system, all the particles would just go to the bottom. What's the other current? Yeah, diffusion, okay? Diffusion opposes this. Why? Because J diffusion, like Fick's law, is negative d rho dx. And it says if you have all those particles at the bottom, there will be some tendency for some of them to come up. Cool? And so the balance between these two particle currents is what our dynamical equilibrium is, okay? And if we're in equilibrium, what is the sum of these two currents equal to?
Well, some of them can be zero.
Right. Must be equal to 0. Okay. Notice that if we have particles in a box and we don't have gravity, they'll be evenly spread out. Turn on gravity, then there's going to be transitory state, right, where they go from the initial distribution towards the equilibrium distribution. Okay. This is the long time equilibrium condition. All right. Well, we just wrote down this stuff, so let's plug it in. But we know rho dx is equal to negative 1 over kt u dx. And so what we end up with here, negative rho of x mu du dx plus d over kt du dx rho of x equals 0. Okay, and now what we can do is we can factor some stuff out here. We can factor out negative rho of x du dx. We multiply that by mu minus d over kt equals 0. And what is the non-trivial solution to this equation? Anybody? How can we get stuff on the left-hand side? Not trivial like that. This is for mobility is equal to d over kt. Okay, this is the Einstein-Smolkowski equation. Why did I bother bringing this up? Does anyone find this relationship surprising, interesting, obvious? Anyone have any comments?
I mean, mu is data.
Mobility is
Well, when I'm data, I don't know that.
Yes, but let's keep it in this form for a minute. Okay.
but shouldn't our mobility be our diffusion as 1 less pi like thermal motions? Like I feel like that statement should be a thing. Not just like, okay. Maybe I'm going in circles.
Okay. So where did we derive this from? We derived this by saying, okay, we have a particle, and it has some thermal energy. We're going to drive it with some force F through a medium. Okay? Cool? It's going through a medium, so we know it's going to reach a terminal velocity. Right? And we said, okay, our mobility is just that terminal velocity over our force F. Okay? This is what our mobility is. You have a particle in your system, you apply an external force to it, it starts moving, it reaches terminal velocity. Your mobility is just that velocity over the force. Cool? That's the left-hand side of this equation. How about the right-hand side of the equation? When we're talking about diffusion, what picture do you have in your head? This is a diffusing particle. It's a random walk, right? And so it's taking all these jumps, and we saw that you can painfully calculate not the mean position, because the mean position is 0, but the mean square position. And this is equal to 2d times. Cool? So that's the right-hand side of this equation. So what Einstein-Smolkowski tells us is that these two different behaviors are intimately connected. Okay? In one case, we're talking about applying an external field to a particle and driving it through the system. In the other one, we just have a particle there, no external field. Okay? And it's jumping around due to interaction with other particles. We can characterize that by a diffusion coefficient. When Einstein-Smolkowski equation tells us that, well, that mu is just that d normalized by Is everybody okay with that? Is it obvious to people that this experiment is somehow directly related to this experiment? Yeah, you're on the right track. We've talked about the reason why. It's a here.
Oh, it's just the wait. Not great.
Two words. Each one of the words describes one of the terms we add to our equation of motion to get one of them. We added a fluctuation term. And we added a dissipation term. This again is a fluctuation dissipation term. Yeah? This is fluctuations, right? These are just being kicked around. Well, why does this guy reach terminal velocity? Because at a certain point, the energy we're putting into this particle is being dissipated through the medium. Cool? A fluctuation dissipation. And again, a simple physical picture for this is exactly like Sarah was getting at. If you consider a particle in a system here that finds itself experiencing some force in this direction, some acceleration in this direction, it does not know, and the system does not know, whether that is due to some internal kick from the system or whether it is due to an external will respond in the same way. Cool? Of course, this is only true when your external field is not too big. Okay? Such that the energy can be dissipated at such a rate that this is true. Okay? If you had a huge field and this thing starts, totally distorting the medium in front of it and creating turbulence and adding like heating up everything, this isn't true. Okay? Then it's not true that this is the same as having a big kick. Okay? In other words, we've got to be in the linear response. Cool? Yeah? One of the goals of this course is to give you some feeling for fluctuation dissipation. Okay? And this is in my mind, the most dramatic example of fluctuation dissipation. Because to me, it is not obvious that this experiment is the same as this experiment. Okay? That if you did this in the lab and you did this in the lab, that you'd be like, oh, I don't even need to do this. Oh, because I can get D just mu. Okay? That would not be obvious. Cool? Yeah? All right. So that's Einstein-Smolakowski, and it's a great example, well, really a realization statement of fluctuation dissipation. Cool? Okay.
But this is equivalent to the previous one we saw with theta, right?
Yes. But what's nice here is that you really have this external force versus.
Zeta is the reciprocal of that?
Well, because D is equal to KT over zeta, so yes. Yeah. Cool. Okay, so we're pretty much done with the first order equation. It's so easy to handle. Okay? So the only thing we have to talk about is how we can actually simulate this. So simulations of the first order equation, let's do what we were doing before with the second order equation, but now let's just drop the inertia. Okay? What do we do if we have that? It means that V with RT theta So,
There's a dot, right?
where?
Oh, no, there isn't a dot. Drop.
No, drop, that's the term, drop. And so if we want to discretize this, let's make our problem simpler by getting rid of R, putting in what we know about R, okay, to get the right variance in R, so that our noise can just be from a distribution that has a variance. Okay, kind of the worst Z ever. Cool. And what do we know? Well, this is 2kt zeta over zeta squared, because I can pull that from the other side and pull it below. And we still have this delta t that comes from discretizing. Cool? It's exactly like we were doing for modular dynamics, except now we just have it, we can go right from the velocities. Cool? Okay. So what does this mean?
That psi is unit variance and zero mean. Anything, right?
Yes. That's horribly messy, I'm sorry. But it's our usual stuff, okay? That the square of this thing, okay? Well, the correlation of the average correlation of the noise, okay? If t prime is not equal to t, it's 0, not correlated in time at all. If we're not in the same Cartesian coordinate, it's 0. So x is uncorrelated to y. Otherwise, it's 1. Cool? Yeah? All right. We want to simplify this. Well, we have z here and z here. We have a zeta there and a zeta there, so we have a zeta in the bottom. What's kt over zeta equal? Yeah.
You're missing an n.
Probably I tend to set those equal to 0.
Maybe not.
No. No.
No.
Because again, the n is with the
The accelerator.
yeah. All right, well, this is a wonderfully simple algorithm.
How did the 1 over delta t become a... Oh, okay, yeah. Yeah. Oh, yeah. Like,
Adjusting the image. There you go. All right. So our code is super easy. Okay. All we're doing for a single particle here, we're defining a prefactor here, which is just 2d over dt. And we'll see why I'm doing it this way in a minute. Then we draw a bunch of random numbers. The velocity, okay, the prefactor times this gr1, our Gaussian random number here. Then x is just x plus v times v. Cool? So that is exactly the same. Okay? Yeah? So what do you think this motion is going to look like?
Very similar to the
Is it?
the random walker.
You're just
So
thinking that-
longevity dynamics, we have a particle here that's traveling at velocity. It gets a kick like this. What happens?
In walkabout,
Yeah.
slow it down.
Yeah. It slows down, right? And then starts going in this. Cool.
Top here.
What happens in Brownian dynamics?
Or are we just instantly changing the velocity?
Yeah, you're at this position. You don't have velocity there. The next thing that happens to you is you take a jump according to that shape. Okay, and then you're here. You don't keep some velocity from this. You take another jump. Okay. Yeah. Remember, in longevity dynamics, we had these short-time correlations, right? Brownian dynamics, we have completely uncorrelated jumps. Okay. Math, this is a true meter problem, right? It is it's a Markov chain, right? Each state, right, is only you jump to the next state. There's no correlations anywhere. Cool. Yeah. So that's what we expect the long-time version of longevity dynamics to look like. When you're zoomed out so that you don't see those short-time correlations, then it looks like that you have something that's jumping here and jumping here. Okay? But when you get down to it, you have this ballistic stuff. You have none of that in Brownian dynamics.
When you set a maximum like jump distance,
Okay, great question. So this is one of the fundamental differences between longevity dynamics and Brownian dynamics. Okay? So in my simulation in longevity dynamics, what did I take the time step? Does anyone remember? Pardon me? You're just guessing?
I guess that's.
Does anyone else just want to say a number? No, it was 0.01. Okay, which is a typical time unit if you're setting everything equal to 1. Okay. Brownian dynamics, there's really no limit on what delta t is. Okay? It can pretty much be whatever you want. You can have really big jumps. That just corresponds to the system evolving hard. Okay?
so if one, like is every jump the same distance then?
No, because we have this random term there.
So theoretically, if we're making did a jump that was across the entire screen, it could do that in a single time step.
But this falls off as a Gaussian, right? So that's exceeding the unlikely.
But could
Given a big enough time step. Yeah.
Yeah. Okay.
So do you usually just make t equal to like 1 or something and just kind of
Yeah, it depends on your system size and how fine you want to look at the dynamics. Okay. But this is a limitation that BD doesn't have, but longevity dynamics does have, okay? And so let's just see why longevity dynamics has. So longevity dynamics is mv dot. Let's just say it's traveling at some velocity, and we're going to ignore the random term for now, okay? This is longevity dynamics, right? What is this equal to? This is equal to dv dt, when we discretize it, equals negative gamma v naught. Okay? So if I'm going to discretize this, I'm looking at my v at whatever time step I'm at, right? I take my zeta over m, and that's equal to my gamma. Cool? If I want to solve this, then v is equal to v naught, because delta v is v minus v naught, minus gamma v naught delta t. And so v is equal to 1 minus gamma delta t V naught. So what happens? Delta t is bigger than 1 over gamma. So remember our picture here. We have a particle traveling along some velocity. So first of all, let's take dt, delta dt to be much less than 1 over gamma. Okay, that means that this is some small number, right? And so if this was our original velocity, at the next time step, the velocity would be a little bit less than that, which is what we would expect. We have a damping term, right? But what happens when delta t is greater than 1 over gamma?
Like, or it goes to a negative term, actually.
It goes to a negative term. Okay.
We have a negative velocity then?
Yeah. So what happens if we make our time step too big is that we're originally traveling like this. Okay? And we're taking this moment in time, we're trying to dampen it so much that we've actually made it go backwards.
Oh, that would break anything.
Exactly. Okay? Unstable.
Is that not closer to Kyle Brownian dynamics?
Brownian dynamics, you don't have this velocity in there.
Yeah.
Brownian dynamics, it just jumps around.
Yeah.
There's no velocity like this.
It would end up being like a jump, more of a jump in motion.
Right, but what happens if you have this in your system? Your velocity like this is damped. You can actually get like a bigger velocity going this way. Okay, so it's numerically unstable, and everything's going to crash. Okay, so in algebra dynamics, there's a maximum time step. Okay, typically delta t must be less than, and preferably significantly less than 1 over gamma. What is 1 over gamma? That is mass over theta. Okay, do you guys remember what gamma is in words? What's gamma? Collision frequency. The collision frequency. So 1 over the collision frequency is collision, the time between collisions, right? So you can also call this like the relaxation time, right? And so if your time step is bigger than the time between collisions, you're going to have problems. Okay, cool. Algebra dynamic, Brownian dynamic do not have this limitation. Okay.
Brownian, do you have to scale the time step with the jump distance again? Okay. If I increase the time step, then I should take larger jumps, right?
Yeah.
Does that fall out after the integration?
Yeah, because when you plot delta x squared versus t, you're going to get the same. Which means your diffusion coefficients. Yeah. Cool. Okay, so our code is super simple. What does it actually look like? Well, again, we can run through the same program we use to calculate the mean square displacement from algebra dynamics, because what's the difference? We're just looking at the position. And this is what we get. So this should look familiar. I'm using the oversampled method here, so I have my smooth correlated noise in there. But this is what I expect, the solid line, and red is what I get. Pretty good. Cool. If I do the log-log plot, I get this. Blue is what I expect if it's diffusion. Red is what I expect, is what I get from the simulation. So does anybody remember what this line corresponded to in algebra dynamics?
That was the line indication of course.
Yeah. In algebra dynamics, we had this transition from ballistic to diffusive motion. So it was originally going as t squared, and then it folded over, it transitioned to going as t. So we saw this transition between ballistic and diffusive motion. We see that here? No, it's diffusion all the way down. Okay? And of course, we can do the same thing by calculating multiple particles in one simulation and just keeping track of the average x value and the average x squared value. Okay? And again, from those moments, we can calculate the mean squared displacement, and that's what we get on a plot like this. Okay? And again, previously when we looked at this and we zoomed in, saw that it was actually quadratic here, but now it's linear all the way down. Cool? Okay. Oh yeah, okay, cool. So this is the fun part. So all of that is just to show that we get the same answer, okay? So now let's have a look at the distributions, because remember we said something about the distributions. So this is another program, BD Fokker, okay? Because the solution we came up with, the Gaussian, that is the Fokker-Planck equation when there's no zero drift, okay? If you hear Fokker-Planck, think of the solution to that PDE. Cool? The Gaussian that showed how the distribution was spreading. Okay? So if we want to compare the results from our simulations to that, what we need to do is do a simulation for a whole bunch of particles, right? And then we're just going to do a histogram of how many are found at various x positions of the function. Yeah? Cool? That's what this code does. So it does it for 10,000 particles. It just does the Brownian dynamics. And all it does is it takes a distribution for the number of particles between x equals 0, x equals 1, x equals 1, x equals 2, etc. Okay, so our bin width is just going to be cool. Okay. Okay, so I have output that data as a file called BD row, and all that is the first row is just the number of particles in each bit. Okay. Second one is at the next time step, the number of particles in each bit. Okay. Cool. And to make sure things don't go to negative values, I've arbitrarily offset this by 500. Okay. Which I can then correct for. And I just got email from Sarah. She's emailing me while she's in.
No.
I'm just kidding. Okay. And then also what I'm going to do is I'm going to overlay on top of that the Fokker-Planck equation. Okay, which just is that distribution that's Gaussian in x, where the variance spreads linearly in time. Okay, and this is what I get. Pretty sweet agreement, right? So that SPE the random term is entirely equivalent to the diffusion equation describing the evolution of the distribution. Cool? Let's start this from the beginning. The agreement is totally great.
That's awesome.
Neat. Hey. Okay. And so these things, remember, are quite different. This guy is a stochastic different equation that allows you to simulate the trajectory for any particular particle. Okay. This is the distribution of particles. This tells you nothing about what an individual particle is doing, but it tells you how the distribution of particles is evolving. Cool? And they're totally exactly. Okay? With R being defined by that. bracket R, and the 2AT. Cool. Neat, eh? All right. So this is what we've done. Remember, all we've done is we started from Newton. That equals MA. Added fluctuation dissipation to our equation of motion. We did the second order. It was quite complicated to work with. We just did first order, all of it today. Okay, easy to work with. And that's the gravity dynamics. So MD, LD, ED. All right. Anybody want to guess what our next step is? Because we're kind of coarse graining out, right?
0.
0.
No.
Write it down. Look at that. Okay.
I'll do coarse grain solver stuff.
No. Not yet. Anybody?
What the distribution requirements of
No, so we kind of did that right here. Yeah. We'll come back to applying an external force later and see how that changes.
Compound part.
Nope. So I want to stay with a single particle or a bunch of non-interacting. Think of another algorithm, another way of simulating this. Monte Carlo. Okay. Because when we dropped the inertial term, we went from having these velocities in there that smoothly change with time to really having no velocity and just these jumps. If we just have a particle jumping around, why are we bothering with all these things like taking this random number and this distribution according to that? Let's just do it totally probabilistic. Let's just have the particle at some position and just have some probability that it jumps in another direction. Okay? So we move away from the equation of motion idea altogether, and we just take a totally probabilistic version. And that will be Monte Carlo. Okay? And we'll see that it is also identical, okay, with the discretization, of course, to what we would do. Okay? So that'll be the next step, and we'll start that next week.
Are we doing a thing tomorrow morning?
Yeah, we'll do a thing tomorrow morning.